The initial energy I used to start this class has diminished. But nevertheless, we shall succeed. So can you hear me, everybody? So before now, we're talking about electromagnetism. And I gave a brief recap of all that you've been doing in electricity. And I'm at the verge of describing the recap for magnetism. You cannot hear me? You can't hear me. Let's try the mic. So we were saying that every magnet has two polarities, the north and the south. And then the magnetic field are being represented by magnetic field lines. These lines are invisible to the eye, so we use imaginary lines to depict the magnetic field lines. The greater the number of lines, the greater the strength of the magnetic field of that magnet. So all magnetic field lines must always proceed from the north to the south pole. So right now on the board, we have just one magnet now. And this magnet, I have just drawn one magnetic field line. I'm going to draw more. And then we learn about the characteristics of these lines. These lines move about, they are parallel to each other. They can never intersect. If they intersect, it is not possible, like for example now, if this line touches the other line, it is very, very, very wrong. In fact, it is not possible because magnetic field lines are said to never intersect each other. In fact, they must be parallel to each other. So, for this example, I have just three magnetic field lines. You could see that at the middle, they are well spaced out. But at the edges, they are closely packed together. This signifies that the magnetic field strength is closer at the edges of the magnets. Now, magnets have characteristics that is common. We have seen them before. If you bring two magnets together that have different polarities, you are going to experience a force of what? Attraction. For example, we are having north and what? South. There's always going to be a force of attraction between the north and the south pole. Now this force of attraction, see, strength or every magnetic field, it is a vector quantity. It has magnitude, it has direction. And there's a very, very important equation that you should know, that the force of magnetism, F, is always directly proportional to what? The strength itself. So magnetic force, F subscript M, is equal to what? B, the product of B, I, L, S, SI, where B is always known as what? The magnetic what? Flux density. I don't know, you must have given you this formula in the last class, right? Isn't it? Then I is always known as what? The current. L, the length. And then theta is always what? The inclined what? Angle.
Sorry, sir. So please, in the next 4 minutes, we are not going to waste our time on this. In the next 4 minutes, we've already shared the group in your class. Kindly share with your friends. Whether you guys on time, do it on time. In the next 4 minutes. In the next 4 minutes, please, I'll go to your phone. Share it with your friends. Show me what. Sharp. 1 minute. One minute.
So let's continue. Also, the field or the force experienced by magnetic field is also related with this formula Q V B sine theta. Now, what's the difference between this and this? The quantity of the parameters here, Q, is usually a charge of a proton. V is the velocity of the charge. B is still your magnetic flux what? Density, and this is always measured in what? Measured in Tesla. Theta is always the inclined angle between the charge and your what? And your horizontal. So the inclined angle, the velocity of the charge and your what? Magnetic flux. You can see, for example, if a charge is coming in this direction to form an angle theta, the velocity of this charge to form an angle theta with this. If this charge, for example, or if this angle, for example, is what? 0, it then means that this formula becomes what? F equals to what? QVB. But if this angle theta is what? 90 degrees, it means that your magnet or your force experience is at its what? Maximum. The force F will be at what? Maximum. F max. Why are we learning all of this? These two formulas, we will come across them in your JAMB. And they are all under the what? The topic electromagnetism. Now, we have not dealt with the definition of electromagnetism. We've only just talked about what electricity is, the various aspects of electricity, and then what magnet is, and the various aspects of magnetism. Who in the audience can tell us what the definition of electromagnetism is? There are just two words there looking at you. One can simply say this is the study of electricity and what? Magnetism. As simple as that. Then what more can you say about electromagnets? It's a field. It's a vector quantity. Since electricity itself is a vector quantity, magnetism is also a vector quantity. Now, in electromagnetism, the total force that is going to be experienced is going to be the sum of the force experienced in electricity and that of what? The magnets that you are using. So I can say under electromagnetism, let me give a definition to this. I can say that this take a look at this. The joint interaction of electricity and what? Magnets, which produces what? Which produces the joint interaction between electricity and magnets, which produces a what? A mechanical force. So what are we saying? We are saying that the force experienced in electromagnetism is a total combination of the electrical force, which is also a vector quantity, and what? The magnetic force, which is also what? A vector quantity. So, but we know that the electrical force is defined by what? Who can tell me? Who can tell me? It's defined by a charge, QE. What about the magnetic force? What about the magnetic force? It's also defined by a charge, Q, V, and B. It's only under the magnetic force that you can see magnetic flux density, velocity, and what? Charge. It means that the magnetic force is directly proportional to the charge, the velocity, and the what? The magnetic flux density. Some of you are looking at me that what is magnetic flux? I told you that under magnetism, we represent the fields, that is the force fields in magnetism with what? Imaginary lines. Those force fields, they are also known as what? Magnetic what? Flux. The stronger they are, the stronger the magnetic flux density. It simply means that is the strength of the what? Of the magnets. A magnet with greater magnetic flux density means that it is a very strong what? Magnet. So the total force experienced is this. We cannot say that the total force experienced F is equal to, you have your Q, there's Q here, there's Q here, you bring it out here, you have your charge, small letter E, plus what? V, B. By the time we start working with some real life practical examples, these concepts will be real to you. But now, we have not told us what happens from this definition. It says when you bring electricity and magnets together, it produces a what? A mechanical force. Who was the first scientist to experiment with this? His name was Ørsted. What did I say? Ørsted. By then I wasn't born. What did Ørsted observe? He observed that when he placed a bar magnet inside a solenoid, I hope you know what a solenoid is. You should have the prerequisites. When we're talking about magnetism, you observe that a solenoid is a what? A thin wire wound. A magnetic material, a current carrying conductor wound and connected to a current. So what did Ørsted do? He placed this magnet into what? A solenoid. This is what I mean by a solenoid. Hello? Hello? Am I talking to somebody? So he placed his bar magnet into the solenoid, and he observed that there is a mechanical force that was produced by this interaction. This solenoid provides what? Electricity. It was connected. When connected, in his own experiment, he used a battery. This is the switch. And he connected it and discovered that something extraordinary happened. He discovered that when he did this pole or this side of the solenoid acquired a what? A correspondent north pole, just like that of the what? Magnet. And he experienced a force of repulsion, because if this position acquires N, it will also have a what? A force of what? Repulsion. So as he was trying to push this magnet into the solenoid, the magnet was also fighting back to go out of the solenoid. So he observed that there is an equal and opposite what? Reaction force. And he said to himself, okay, I will do this experiment over and over again. He pushed it, let's say he pushed it forward, the magnet and the solenoid started having what? Force of what? Repulsion. And when they were having this force of repulsion, he discovered that at this point of interaction between the magnet and the solenoid, there was great field, magnetic field what? Strength. This principle that he discovered was now further worked on by Faraday. Faraday now connected his own, not only to a battery, to what? To an alternating what? Current. So when he did this, he discovered that this interaction that is happening, if it continues to occur, it is going to produce another type of current called what? Induced EMF. Hello? Induced what? EMF. So in this experiment, the more you push this magnet in and out, another current or potential difference is being produced. So you are the one producing this kind of current. We call that current an induced EMF. And this process was called electromagnetic induction. So what is an electromagnetic induction? It is a process of producing induced current when a magnet is introduced into what? An electric what? Field. It could be vice versa. Somebody can say when an electric field is introduced into what? A magnet. So if you choose to push the electric field into the magnet, or you choose to put the magnet into the electric field, you are still doing the same thing. So this is a process of producing what? Induced current or EMF when an electric current is introduced into what? A magnet. Faraday said something. He now said, okay, I'm going to propound a law that will govern this process. And what the law states, it led us to find or discover that law is the first law of what? Faraday's first law of what? Electromagnetic what? Induction. Is there anybody in the audience that can state Faraday's first law of electromagnetic induction? Is there anybody? Can I see your hand up? Is there anybody? Anybody? Nobody? Any idea? Now, this induced current or induced EMF that we're talking about, Faraday discovered that the induced EMF that is being produced is always directly proportional to the rate of change that is being produced. The rate of change. What do you mean by rate of change? The more you put this magnet in and out the electric current, the more induced EMF that you do what? You produce. But we also discovered something, that when you are doing this, the current that you are producing moves in such a direction as to oppose the motion that is producing it. So this equation I wrote on the board now, if you remove the sign of proportionality, this induced EMF or induced current is equal to what? Minus N d phi dt. I is the induced EMF. Induced current or what? EMF. The phi dt is what? Rate of change of the what? Magnetic flux linkage. and then what else again? Now, I now remove the sign of proportionality and I put n. N is defined as what? The number of what? Turns. So the amount of induced EMF that you can produce is directly proportional to this. The rate of change of the magnetic flux linkage, the number of turns, n. Now there is a minus. Does it mean that the induced EMF you are producing is lesser? No, it doesn't mean. In fact, what it means is that this induced EMF that you are producing is moving in such a direction so as to oppose the motion. So we have stated first law or Faraday's law of what? Electromagnetic induction. I don't like using English to define my laws. This equation alone has stated the first law. If you understand mathematics, you will understand what? Physics. This law, for those of you that like writing, states that the induced EMF produced is directly proportional to the rate of change of the magnetic flux linkage and the what? Number of what? Turns. Those of you that like English. But to me, after stating it, I will put the equation. This one carries more mark than that English you are writing. After stating the equation, I will put down my what? Parameters. The reason why we are having a negative sign is because the induced EMF that is being produced is moving in an opposite what? Direction. It's moving where? In an opposite direction to the force that is producing it. So that leads us to the second law that is under electromagnetism, and that second law is called the Lenz law. So what does Lenz law state? Lenz law says that the induced EMF is moving in such a direction so as to oppose the motion producing it. So you cannot talk about electromagnetic induction without mentioning these two laws. Just as we started in the beginning, when I was talking about electricity, under electricity we have different laws. We have Ohm's law, we also have Coulomb's law, and the rest. You must have known that. I won't go back to that. Under magnetism, we also have their own law. Law of repulsion, law of attraction. We also have other laws that govern what? Magnetism. But when you bring the two together, this is the two laws that govern them. Faraday's law of electromagnetic induction and then Lenz law. You must have it at the back of your head. Some textbook, we want to write Faraday's law using the letter E, capital letter E. Is it different? No. Because the currents or EMF, you see the definition of electromagnetic induction, the production of current or what? EMF. Current is I. I use I here. So if you come across a definition that shows E and you are having E is directly proportional to what? The phi dt. Are you going to be scared? It also means that here, this electromagnetic induction process is producing what? Potential difference or EMF. Hello? Hello? What more can I tell you? I can also tell you that this EMF or this current that is being produced is also related with this formula. I equals I naught sine omega t. Or if you are using EMF, E equals E naught sine omega what? T. Those of you that are doing JAMB, you will come across this. I is current. E is what? EMF. I naught here is the maximum current that can be produced. Omega, angular what? Angular velocity. Where T is what? Time. So for the second one, E is the EMF. E naught, maximum EMF. Omega, angular velocity, and T is what? Time. In further classes, I will explain how to derive these two equations from the first law of electromagnetic induction, and also from one law that we wrote down here for what? Magnetism. There's a way you can derive these two from this law and from a law that states that what? That states that found in various electrical devices all around us. For example, your radio is an example of electromagnetism. Your loudspeakers is also an example of what? Electromagnetism. Your generators are also examples of what? Electromagnetism. What is going on in all of these devices I've mentioned? There's an interaction between electricity and what? Magnetism. Most times, for you to produce an induced current, you must need the following. You must need a very strong magnet. Most times, electromagnetism is found in electric motors. Another real life application, electric motors, where you have your AC and your DC. They are simply your electric generators. Your AC means alternating current generators, and your DC means what? Direct current what? Generators. The processes of producing those type of current is also a process that obeys the law of what? Electromagnetic what? Induction. Hello? Hello? In your exam, you will always see a diagram like this. They will draw an electric motor for you. They will draw an AC and a DC motor for you. Both of them have similar composition, but there is just a very slight difference. Now I told you, for you to produce an induced EMF, you must need a very what? Strong magnet. You must also need a very good current carrying conductor as your what? As your magnetic material. What did we say depends? What are the factors that makes us to be able to produce a very strong current? We said you should have what? The number of turns, the rate of change of the magnetic flux linkage. You cannot have all of this if you have a weak magnet. You cannot have all of this if you have a weak magnetic material. What am I talking about? If you take a look at the electric motor diagram, just hold on. Application of this electromagnetic induction is in your what? Electric what? Motor. For example, you're always going to have this. What have I drawn? I've drawn an electric motor or a DC motor. In this diagram, this type of magnet that is here is called a horseshoe magnet. Hello? This is the north and this is the south. So this is called a horseshoe magnet. Now, in between this magnet is a rectangular iron material, a rectangular soft iron material. We call it a soft iron core. What did I say? A soft iron core. And most times, it is always iron that is being used because of its magnetic properties. Remember, when we were talking about magnets, you know that iron is only the material that you can use that can attract magnets easily, isn't it? It retains its magnetization even after you have removed the magnet, isn't it? So iron is preferred as the strongest magnetic material that will be used in the production of your electrical motor. So look at this material here, A, B, C, D. This one that is lettered A, B, C, D. This material is made up of iron. Are we together? Soft iron core. Now we call this in an electric motor. We call this the The armature. We call this the We call this the So this armature is usually made up of a soft iron core material. Now, what is this device used for? What is it used for? It's used to convert mechanical energy into electrical energy. And one of such device in your house is your generator. When you go to on your generator, you are the one that use your mechanical energy first of all. You pull it. When you pull that generator, something happens inside it. Something starts to turn. What turns inside it is your armature. There's always a armature. Some of you call it alternator. That alternator is in between a very strong magnet, and all around it there are windings. There are windings around it that makes this process to work. Now, this armature works on a principle of what we call couple. And what is a couple? A couple is when you have two equal and opposite reaction forces. So what happens when you on your electric motor? The mechanical energy or the mechanical force you use into this makes this motor to turn continuously. And in this diagram, I have what we call, here is called the carbon brush. We have two carbon brush. So each working principle follows the principle of electromagnetic induction. As this armature turns continuously, it is already a magnetized material. The magnetic forces from this north and south pole is acting on this iron, making it to do to turn back and forth. That turning back and forth is what we call the couple force or the torque of this couple. When we hear the word couple, we use torque instead of force. You understand? It produces a torque. That torque ignites these carbon brushes, and this carbon brushes invariably releases alternating or induced currents. That induced alternating current goes into your house in form of This is just a very small example. We have the one for AC. Now, there is this middle part I'm going to highlight for you, which is always important. It comes out in JAMB. This part is called the split ring. This split ring does what we call on and off. By the time I draw an alternating generator for you, you see that the diagram is virtually almost the same, but the only difference is that this split ring will be replaced with with a slip ring. So in this is also known as a DC motor. So if you want to convert this DC motor to an AC motor or a DC generator to an AC generator, all you need to do is to change the split ring into what? Slip ring. Every other thing remains the same. The both of them are working under the principle of what? Electromagnetic what? Induction. I'm going to mention 3 other devices that you go and study their working principle. Those 3 devices, they also work with the principle of electromagnetic induction. One of them is okay. I think my handwriting is too small. So one of them is called the what? The moving coil galvanometer. This works with the principle of what? Electromagnetic what? Induction. What does the moving coil galvanometer do? It measures little amount of currents and potential differences. But this composition, the structure of that moving coil galvanometer has a very strong magnet in it, and then it has a core. It also has what? Windings, almost similar to this, but it's just that it is connected to a pointer. It is the pointer that gives us the reading of a moving coil galvanometer. Because it is a measuring instrument, it is very, very what? Sensitive. And because it measures small amount of current, the sensitivity of the galvanometer is the ability of the galvanometer to measure what? Little amount of what? Current. Another device, like your battery is done. Another device that works with the principle of electromagnetic induction is your what? And then the third device is your what? Transformers. So all of these, they work under the principle, or using the principle of what? Electromagnetic what? Induction. You already know what a moving coil galvanometer does. I was talking about something of the sensitivity. What improves the sensitivity of this is the strength of the magnet that you use. Anytime you perform electromagnetic induction and you put or introduce a galvanometer to the meter or to the circuit, the needle of this galvanometer must always indicate movement or deflection whenever a magnet goes into what? A solenoid. If this magnet goes into the solenoid, for example, this is 2 watts. It goes into the what? Solenoid. This galvanometer will indicate. If it goes away from the solenoid, this galvanometer will also what? Indicates. Showing you that induced current has been what? Produced. If you continue to put it in and out, just as the process of electromagnetic induction dictates, the galvanometer, the pointer of the galvanometer will continue to do what? Fluctuates. It will continue to do what? Deflects. In all these devices that work with this principle, the factors that affect the production of induced current are as follows. the strength of the magnet. If you want to produce large amounts of induced currents, you must always have a very strong magnet. Number two, if you want to produce large amounts of induced current, the number of turns the greater the number of turns, the greater the induced current that is being produced. Number three, you must always use a laminated soft iron core in the production of your induced currents. Why do I use the word laminated? By the time we are studying about transformers or the way transformers are being made, you discover that whenever you have a current carrying conductor and the windings are across it, there is a way we arrange these windings such that energy will not be lost. When you are producing induced current, work is being done, energy is being created. So to prevent energy loss, we must always use the laminated soft iron core. Another factor for producing or that increases the production of induced current is the area, the cross-sectional area of the current carrying conductor. Switch off that phone. Who has this phone? So if all these factors are met, your induced current will be great. Why do we want to produce induced current? Why? All the current that you are using at home, they are all induced, be it AC or DC. Take for example your transformers. Sit down and join this. Take for example your transformers. What do they do? What is their structure? What is their composition? How do they obey the law of electromagnetic induction? What are their processes? A transformer is an electric device that either steps up current or voltage or steps down current or voltage. It is used for stepping up or stepping down. When we draw the composition of this transformer, you're going to see that truly it obeys the principles that abide by electromagnetic induction. Inside the transformer, this is how it looks like. A transformer usually has an input and an output. Hello? A transformer usually has an input and an output. But I want to show you that even in the makings of a transformer, it also obeys the principle of electromagnetic induction. Inside the transformer, we have this. The input is also known as the primary, while the output is known as what? The secondary. This transformer is also made up of a what? A laminated soft iron what? Core. Look at this. This material round like this. Inside the middle of this soft iron core is a very what? Strong. It's a very what? Strong magnet. Around the laminated soft iron core are what? Current carrying conductors that are wound along the input and also along the what? The outputs. So if you don't have a strong magnet in the transformer, you cannot produce a greater what? Induced current. If you don't make use of a soft laminated iron core, you are going to have a lot of energy what? Losses. Even the production of your induced current will be what? Low. So basically, what does this do? How can you know that a transformer is step up or a transformer is what? Step down? Question for the class. How can we know? We said it is an electrical device that either steps up current or potential difference or steps it down. So how can we know? Hello? Anybody, how can we know? The number of what? Turns. The number of turns in the primary and the number of turns in the secondary is going to determine if that transformer is a step up or a what? A step down. Now, if I have more turns, in some texts they can use the word windings. In some of your textbooks they use the word windings. Windings is the same thing as what? Number of what? Turns. If, for example, in your input or your primary, for example, I have just three turns, for example, 1, 2, and 3. But here I have more than 3. What kind of transformer is this? Step up. So number of turns in the primary was lesser than the number of turns in the secondary. Or somebody can say number of turns in the secondary was greater than number of turns in the primary. Can we see that? So if it were to be the step down, the reverse would be the case. But the series transformer, it is governed by the principle of what? Electromagnetic induction. We have so many other devices that work under the principle of electromagnetic what? Induction. The binding formula for this that we can use in solving transformer working or problems in transformers is ES over EP equals to what? NS over NP equals to what? IP over what? IS. What is ES? What is EP? What is NS? What is NP? What is IP? And what is IS? Where ES is the what? EMF in the what? In the secondary. EP, the EMF in the what? NS, number of turns in the where? NP, number of turns. This formula can also be written as Vs Vp equals Ns Np equals Ip Is. Do you see that the relationship between the voltage and the current is inversely what? Proportional. But the relationship between the voltage and the what? Number of turns are directly what? Proportional. The greater the voltage, the greater the number of what? Turns in the secondary. The greater the voltage in primary, the greater the number of turns in what? Primary. But is that the same when you talk about current? Inverse what? Relationship. That is under the workings of a what? Of a transformer. A transformer, just like any other device, is a machine, and every machine has its what? Efficiency, isn't it? So the efficiency of a transformer is also given by this formula. Output over what? Input times what? 100. And in this case, what is the output? The output is all of the secondary. So the efficiency is given as what? Is Vs all over Ip Vp times what? 100. If you are going into battle, if you don't carry your weapon, if you don't carry your shield, how long are you going to last in that battle?
0.000.
No knowing physics without formulas. Formulas are your what? Weapon. Have I talked for 1 hour now? Have I talked for 1 hour? It's up to 1 hour I've been talking, right? Question time. Question time. Not just nonsense question, no. Question on what we have been talking about. Now, you can either take the question from your past question or you take the question from your head. It's up to you. I have my past question here. I'm talking to you that you are writing JAMB. I have my past question. Open your past question. Bring out questions from electromagnetic induction. Bring out questions from transformer. Bring out questions from electricity. Let us pieces it. This is where I would like you now. For those of you that will give me questions, this is where I will do what? Like, this is where I will know you. And once I know you, you are getting A. Once I know you, you are getting 98 in your JAMB Physics. But if I don't know you, what do they used to say? Or your... What do I mean by know you? If I develop special interest for you, you go no book walai. Your head will open. You begin to what? To see things. I need what? Question. So that discussion we're having now is the question. I have a question. Yeah. Come again. Stand up. Let me hear you. Page 1 to be different. This board, Jerry. Stand up.
2547.
Yeah. So, yeah. 2025. Question 9. Can we have a reader? You can read it for us. So this is JAMB. Oh yeah. Somebody say read it out. What page is this? Page 74. What does it say? What is that, everybody? What the hell? Read down for me, Jare. Oh yeah. Read it out. Question 9. Oh yeah. Photoelectrons. Is it the same thing? Photoelectrons. Under electromagnetic induction. Okay, go ahead.
Emitters. Maximum.
That is not under electromagnetic induction. That question is under what? Is under photons. Number 31. Let us stand up and read it. What year? 2025. Question 31. That one you gave us was Einstein theory of photons.
EMF 6 volts.
A cell of EMF. 6 volts. Oh yeah.
6 volts. And internal resistance of 1 ohm.
Internal resistance is denoted with what? Small r. Of what? How many ohms?
1 ohm.
1 ohms.
It's connected to the series.
It's connected in series. That's electricity. Hello. This question is under electricity. Yeah. It's connected in what? Series.
It's a 3 ohm resistor.
With a 3 ohms what? Resistor.
If another identical cell is connected to Faraday, with the force, what is the total current flowing in the circuit?
If another what?
If another identical cell is connected in Faraday, what is the force?
What is the what?
What is the total current flowing in the current?
So we are looking for what? Total what? Current. If another what?
If another electrical cell is connected in Faraday,
In parallel.
the force.
Okay. Another electrical cell is connected in what? You see that? So, it's connected in series or in parallel. If another identical cell is connected in what? Parallel. Okay. So that means we have 2 cells there. Another identical cell connected parallel. So if we have, just hold on. If we have resistance in parallel, how do we add it? How do we get the total resistance? So identical means that the 2 of them have the same resistance. The first one is having big R was what? Big R was what? Resistance there was what? In this question that we just saw, We have big arrow and small arrow in that question. Big arrow was what? Small arrow was what? But remember, they said another cell was connected in what? In parallel. This is how it is. If this is the resistance, another one is connected in what? In parallel. So this first one, arrow is what? 3. But it's identical, meaning that the next one too is also what? 3. Do you see that? So that means if you want to use this formula, V equals to what? I into bracket, R plus small r. This that we'll be looking at will be the total resistance first. So we must find the total resistance first before we can now add to what? Small r. But remember, they are in what? Parallel connection. You must always remember that at the end of your connection, you must invert. This is what? So we want to look for RT now. RT is 1/3 plus 1/3. This is what? 2/3. This is 1/RT. But RT, when you invert, becomes what? 3/2. 3/2 is now what? 1.5. Now we can go and put this 1.5 inside this what? Equation. Can you see it? So V equals I. V already was given to us as what? 6. 6 equals I times, what do we have? 1.5 plus small r, which is what? 1. 1.5 plus 1. 2.5. So we now have what? 6 equals to what? I times 2.5. So what is I? I equals what? 6/2.5. So what is I? 2.4 amperes. Can you see it? Read your question. Open your words here. You see, JAMB is trickish. If you don't understand the question, you get it wrong.
A coil is rotated in a uniform magnetic field.
A coil is rotated in a uniform magnetic field.
Which of the following increases the maximum induced EMF in the coil?
What year?
2025 number 34.
2025 number 34. You see those guys there? You see those guys? Go ahead and read it.
A coil is rotated in a uniform magnetic field.
A coil is rotated in a uniform what? Magnetic field. Do you know what it means to have a uniform magnetic field? What it means is that the magnetic field, the lines do not touch each other. They are what? All parallel. And it also means that that is a force of attraction. It means that this magnetic field, for example, are straight lines like this. This is how the uniform magnetic field will be. So a coil was rotated inside it.
Which of the following increases the maximum induced EMF in the coil?
Which of the following does what? Increases the maximum what? Induced EMF. It's otherwise asking you what are the factors that increase the production of what? Induced EMF. That is the same thing. So what are the options? A?
Decreasing the number of turns.
See, is it what did you say? Decreasing, Abi?
Yes.
Say decreasing. Will it decrease the number of turns? No.
B. Increasing the speed of rotation.
B. Increasing the speed of rotation.
C. Rotating the coil slower.
See, will you rotate the coil slower? The faster the speed of rotation, the greater what? The induced EMF.
D. Using thinner wire.
D. Using wire. If you use a thinner wire, that means the surface area was what? Reduced. We use a thicker wire. So all the factors, cross-sectional area, number of turns, the speed of what? Rotation. Those are the factors that what? Increase what? Induce what? EMF. So in this question, what's your answer? B. B. Very, very obvious. Any other one? Question number 33. This girl has been saying it since. The same year. The same way. Okay, can you read it for us?
Why is soft iron referred as the core of an electromagnet?
Hello. See, All of you at the back, I know what's going on. Continue. You see this life? This life is by what? Is by choice. Hold on. I'll get to you. Oh yeah, read.
Why is soft iron preferred as the core of an electromagnet?
Why is soft iron preferred as the core of an electromagnet?
Magnet.
Why? Why is it that, for example, why didn't you use steel? Why didn't you use copper? Why didn't you use aluminium? The question says, why is soft iron preferred as the what? Coil or the core of an electromagnet? Option. Is it on now? Question 33, 2025. Why is soft iron preferred as what?
As the core of an electromagnet.
As the core of an electromagnet. So option A.
It is a good conductor of electricity.
It is a good conductor of electricity.
It retains magnetism permanently.
It retains magnetism permanently.
It is easily magnetized and demagnetized.
It is easily magnetized and what?
Magnetized. It has a high resistance to magnetic reversal.
It has a high resistance to magnetic what? Reversal. So which is the answer? It's easily what? Now, what that means is that it also retains magnetism. If you say you demagnetize it, if you remove the magnet, the magnetism that it has got when the magnet was there is still in it. That is the main reason. So the correct option to be is supposed to be it retains what? Its magnetism. You see it? That is why iron is being what? Preferred. Any other year? Any other year? Yes. You have a question? Go ahead. Which one? The first one that we saw. Okay, go ahead. It's what they read for me now. It is the internal resistance that was in parallel. But it's what you read for. You told me that the main resistor was connected in parallel. The question said the internal resistance was connected in what? Simple. Your small r, what did you do to it? You work with your small r. Where is the duster there? So in this case, if it was the external resistor that was connected, this is what you do. But if it was the internal resistor that was connected, you use your what? Your small r. So this will be what? 1 over what? Abi? That was connected in what? Parallel. So 1 over 1 plus 1 over 1. You still give you what? 2. 2 over 1, isn't it? 1 over 1. 1 will give you what? 2, isn't it? 2 over 1. But when you invert it, RT will give you what? 2. Can you see that? I have inverted. So if that is the case, 1 over 2, if you invert it, 1 goes up, 2 comes down. I mean? So when you bring this as your small, like put it in the formula, your resistance still remains what? 3 in this case. So 3 plus half. So that's 3.5. Abi? 0.5 plus 3 is 3.5. So 3.5, 6 over 3.5. Here, what will you get? So when you are reading, read clearly, let me know. What they read for me was that the external resistor R was connected in what? Parallel. Meanwhile, it is the what? The internal resistance that was connected in what? Parallel. It has ability to retain its magnetism, not permanently.
Yes, but this option they said
Permanently, no, it's wrong. It's wrong. Its ability for it to retain its magnetism. You know why I don't subscribe to permanently? Because over time, if you don't put on the circuit, it's supposed to be, it retains its magnetism. But this word permanently is not supposed to be there. But in this option of all of them, this is the most correct answer option. It retains its what? Magnetism. Option C. Okay, option B. Retains its what? Magnetism. Do you know that? Hold on. Do you know that when we are producing induced EMF and this induced EMF has been going on, there's interaction between the magnet and the what? The current. Most times energy loss is occurring. Aside from the fact that if the laminated iron core is not properly laminated, there is something that always makes energy to be lost, and that thing is known as eddy current. This eddy current is always produced by a process called electromagnetic damping. Is it on? See this electromagnetic damping I'm talking about now. It is as a result of this property of what? Magnetization. Most times. Hello? Can you hear me? It's going on and off. Most times during this process of electromagnetic induction, after maybe the current has been put off, some of this induced current, they don't go away. What do? They rush and go settle inside the what? Electric carrying conductor. They will stay there. And when they stay there, they are being known, or they are being called eddy current. These eddy currents, they have a lot of heat, and since they produce heat, energy is being what? Lost. So when you have much more electromagnetic damping, energy is being what? Lost due to what? Eddy current. Although there are other sources of energy loss in the process of electromagnetic induction. We have heat loss by hysteresis. We have heat loss by power, I square R. We have heat loss by what? Eddy current. Yeah. Where will I stay? I will stay here. I will stay here like this. So if I stay here to work. Hello? Not working.
I'm tired of this.
So just leave it. Let's continue. Any other question from any other side? Hold on. 1997. 1997. Number what? Number 45. 1997. 1997. Somebody is taking us how many years back? Okay, 1995. Question what? 47. Question 47. 1995. Question what? 47. Hello. The primary winding of a what? Of a transformer has 400 tons. Wait, I told you that you might see the word winding. Two of us. What does this thing mean? Number of what? Turns. So this primary winding that she's talking about is what? NP, isn't it? So how many is it? Wait to 400 turns. NP 400. Oh yeah. And the secondary has what? 100 tons. First of all, don't go ahead. What kind of transformer is this? Step down. The number of tons in the primary is more than that in the. Okay.
If a source of EMF of 12 volts is applied to the primary.
Listen, if a source of what? EMF of 12 volts is applied to where? To primary. So that is what? That is EP. Is what? 12 volts. Because it was applied to the what? Primary. Oh yeah?
Secondary EMF will be.
What will ES be? Very easy. The formula is already on the board. ES over EP. What is EP now? 12 volts equals NS over MP. What's NS? Over what? 12. So what do you do? Cross multiply. Over what? 400. You cross multiply. When you cross multiply, ES 400 equals 12 times what? 100. So ES becomes
12 times 100.
So ES gives you what? And it is EMF. So 3 what? Volts. Another one. 1998. Question 46. This is what makes you one of my friends. People that want to what? Learn. Question what? Read it for me. Look at this. A transformer which can produce what? 8 voltage. Now, it can produce. What do you understand by that statement? It can what? Produce how many volts? So what? Who can tell me what that means? It can produce. It can what? Produce. What does that tell you? It's outputs. God bless you. That is what can come out of it. That's what we said. Are you sharing the same brain? It can what? Produce. So the output EMF there is what? 8 volts. Isn't it? So I already know my ES is what? 8 volts. Okay. Look at that word. From. Look at the word. From. Who can tell me what this from means? Input from the primary. Where you see the word? From. So the input is what? 240 volts. So EP is what? Okay.
Supply as an efficiency of 80%.
Has an efficiency of what? 80%. See, in physics, efficiency is also known as mu. Look at this. Mu. So efficiency, mu is what? 80 what? Percent.
If the current in the secondary coil is 15 amperes.
If IS is what? 15 amperes.
Calculate the current in the primary coil.
What is IP? This is what we are looking for. IP. Can you see that? But now we have been given efficiency. So you need to remember the formula for what? Efficiency. And what's the formula? Is up there. So efficiency, look up everybody. Can you see this side? Can you all see? Efficiency is what? 80. 80 equals, we have ISVS. IS ES. This ES is something as what? V. EMF measures the what? Volts. This ES is the same thing as what? VS. This EP is the same thing as what? VP. So we have IS, VS. IS is what? 15. VS is what? 8. Over what? IP, VP. Do you know IP? IP, VP. Where is VP? 240. So you make IP the subject of what? Formula. When you cross multiply, what do you have? 80 times IP times 240 equals 15 times what? 8. IP becomes 15 times 8 divided by what? 80 times what? 240. If you do this, what are you going to get? Me, I know you use calculator. I know you use calculator. 8 here 1, 8 here 30, 15 here 1, 15 here 2. 1 over what? 160. 1 over what? 160. Change it to decimal. And IP should be what? Amperes. 1 over 160 is what? 1.1. 1 point. Now, there's something wrong with this our calculation. Who can tell me? Take a look at the formula for efficiency. Times what? Times what? So we forgot that 100. Can you see that? So the numerator has what? Times 100. Can you see when you cross multiply? This numerator has what? Times 100. Times 100. So if we have times 100, now 8 here 1, 8 here 30, isn't it? 0 cancel 0, 0 cancel 0. So what do we have? Let's write it out again. Let's write it out again. IP equals 15 times 8 times 100 over what? 80 times 240. Oh yeah, now look at it now. 0 cancel 0, 0 cancel 0. Abi? 8 here 1, 8 here 1. 15 over what? 24. Let's reduce it to lowest step. 3 can go. 5 over what? 8. What is 5 over 8? What is 5 over 8 is what? 0.625 amperes. Can you see that? You see now? You forget this 100, you are on your own. See, most of the questions under electromagnetic induction are theoretical, but we still have questions that you guys are not bringing. Look for the question that has magnetic flux density, Tesla, B, length, charge.
So it is theoretical.
Okay.
What causes eddy currents in a conductor?
Very good. What question is that?
2025.
2025, question number 35. Simply says, what causes eddy current in a what? In a conductor. I just said it now. What is the main cause of eddy current? The main cause of eddy current is known as what? Electromagnetic damping. Is it among the options? Yes.
Number 2024, number 20.
Let somebody else also give a question. 24. Which question? 2024. 2024, question 28. Wait, the magnetic flux in a coil. Hello, which quantity represents magnetic flux? Which letter is it? Letter what? B. Magnetic flux what? Density. 2024, question what?
20.
Okay, the magnetic flux in the coil.
Changes from 20 times 10 raised to power minus 1.
Come again, changes from
20 times 10 raised to power minus
changes from 20 times 10 raised to power what? Minus 1. To what? Times 10 raised to power minus 1. Is there Tesla at the back? WP. WP. Like this. Weber. B. Okay, so now this thing that is changing is the rate of change. This same magnetic flux density, they say the rate of what? Magnetic what?
magnetic flux
Changes. Rate of change. So what this girl has just told me now is what? Rate of change. Rate of change is known as what? The phi dt. So rate of change, it has changed from 20 times 10 raised to power minus 1 Weber per second. So what? So what happened to it again?
in 0.2 seconds.
In the time of change. The time of change is what?
0.2 seconds. Calculate the value of the induced EMF.
Calculate the value of what? The induced EMF. And what did we say about induced EMF? Induced EMF is directly proportional to what? The rate of change. Which is what? The phi dt. Now, this phi dt is the rate of change that has been given to us in this time. So in 0.2 seconds, we change from this to this. Who can tell me the change? What's the change? For example, if I say in 0.2 seconds, I change my velocity change from 10 to 8. What is my change? 2. How do you get it? 10 minus 8. Abi? So yeah, I've changed from 20 times 10 to minus 1 to 12 times 10 to 1. So what's my change? 8. 8 times what? 10 is power minus 1. So this is my rate of change. Rate of change of what? In what? 2 seconds. So they say I should calculate what? Calculate what? Value of the induced EMF. And the induced EMF is directly proportional to this what? Change. This change happened Weber, you can see Weber per seconds. This is how they put it, WB, Abi. Yeah. The B has raised to power minus 1. Just like this. So Weber per second. So 0.8 times 10 to the power minus 1 in what? 0.2 seconds. So what are you going to do? You divide it per what? Time. So because the value or the measurement of rate of change with respect to time is Weber per what? Second. So what do you understand by the word per? It means that you do something in every 1 second. Weber divided by second. Somebody can write this as Weber per what? Seconds. So this is the rate of change divided with what? Time. The phi dt. So can we do this? Remember, if you want to do this and you don't have calculator, all you need to do, change the denominator to standard form. 0.2 is same thing as what? 2 times 10 raised to power minus 1. So that the two of them, numerator and denominator, can what? Cancel. So this now becomes what? 2 times 10 raised to power minus 1. This one cancels this one. What's the answer? What? So the induced EMF is what? 4. If it is current, it will be 4 amperes. If it is induced voltage, it will be 4 volts. Another year. 2022. Question what? 26. Alright, can you read it for me? Listen, Oya. Which law? Which law describes the direction of what? God bless you. I love that question. Now, with what? Emotion of what? Field. God bless you. Option A. Faraday's law only tells us about the relationship between the induced current and the rate of what? Change. So Faraday's law is not the answer. Option B. Newton's law of what? Just what Newton's law of what? Nothing. Is it Newton's law? Next one. Lenz law. What does Lenz law say? That the direction of motion of the induced current moves in such a way as to oppose the motion producing it. Any other option again? Fleming's law. The answer is what? Hold on. Fleming is not a law. Fleming is a rule. We have both left hand rule and what? Right hand rule for Fleming. And the reason for Fleming is that Fleming does not only show the motion of the field, it shows the motion of current, it also shows the direction of what? Of magnetic what? Strength. The Fleming's left and right hand rule have the same principle. The only difference is that one is what? Done with the left hand, while the other one is done with the what? Right hand. When the three fingers of both the left and the right are held mutually perpendicular to each other, the thumb is always in the direction of motion, while the forefinger is the direction of what? Current, and then the middle finger is in the direction of the what? Field. The same thing with the right hand rule. Those ones are called what? Rule. They are not a what? Law.
224. That's the question. So what in physics? What differs in law?
Okay, good. Now, in physics, so what's the difference between a law and a rule? A law is something that cannot be what? Changed. It has been stamped. They say you must die. For example, in the past governments, if those of us that are studying governments, I don't know if governments are here, if the government gives a decree and they put it into law, just like they did 1 year, they said if you are not up to 18 years, you cannot go to higher institution. Did it not work? Because the chambers, they went back and they did what? They annulled the law. A law means that it is universal. Everywhere you go, that is how it is. But a rule has condition. A rule has what? Condition. That rule for Fleming, it can only work under what? The principle of what? Electromagnetism. But a law can work universally. Are you getting it now? The same year. Question number 13. You 22? Say 22. Question 13. Can you read it for us? Which of the following? God bless you. Before we answer this question, let me give you the hints of the sensitivity of a galvanometer. I told you that a galvanometer is an electric device that measures small amount of what? Current or potential differences. What is the sensitivity of a galvanometer? The ability of that galvanometer to measure very tiny what? Amount of current. the sensitivity of a galvanometer is improved by what? By the reaction or deflection of the pointer in the galvanometer. If the pointer can react to a very small amount of current, it means that that galvanometer is very, very what? Sensitive. Option A. Number of turns in the coil. Option B. The strength of the what? Magnetic field. Option C. The gaps between the coils. The area of the coil. So which of these is it? Did you say does not or has no effect? So what is it? The gap between the coil. Has no effect, but the rest have effects. And I think I wrote that. The same factors that affect the production of induced EMF is the same factor that will also affect the sensitivity of that galvanometer, because it works with the principle of what? Electromagnetic induction. The stronger the magnetic field, the stronger the sensitivity of the galvanometer. The area of the what? Electric carrying conductor. The larger it is, the larger what? The production of induced EMF. So also the reaction to the pointer of a moving coil galvanometer. Another one. 2024. 2024. Question what? 13. Can you read it? Calculate the energy what? Energy stored
In an inductor.
of inductors. Then millihenry. Millihenry. When a current flows through it. Now, before we solve this question, let me give you a brief history on inductors and inductances. Inductor is an electrical storage device. So, an inductor is an electrical what? Storage device. It stores electrical energy. So also a capacitor. Inductors, they are measured in what? Or inductance is measured in what? Henry. Somebody say Now here they put millihenry. Millihenry, just like when you have meter, you come to what? Centimeter. You never come to what? Millimeter. In capacitance, we say capacitance is measured in farad. So you come down a bit from farad, you come to what? Microfarad. From microfarad, you come down to what? Picofarad. So when you now see millihenry, are you afraid? It's still a measure of what? Inductance. So what's the energy stored? Simply as an electrical storage device, what does it do? It stores what? Electrical what? Energy. So energy stored is giving us what? Half what? Li squared. Where L or where E is equal to what? Energy stored. L is equal to what? Your inductance. In what? In Henry. And then I is your what? So from this question, inductance has been given us what? 10. We are looking, current has been given us what? 8. And we are looking for what? Energy stored. Half times what? 10 times what? 8 all squared. Energy is measured in what? Joules. This answer that you get here must be in what? Joules. What's the answer, everybody? So what's the answer? Solve it. Okay, very good. Very good. Hold on. You see that some of you here are very wise. I love this guy. What's your name? Abdullah. Good. They give us what? Milli what? Henry. And in physics, we must always convert our unit to what? The standard SI unit. So, if this were to be given in Henry, we just use 10. Okay, so what do we do? How can we convert this millihenry to what? Henry. We divide by what? Divide by 1,000. Divide by 1,000.
This is minus 3. It's the same thing.
1,000 millihenry we make what? 1 Henry. So but here we're giving 10. If less, more divide. 10 over what? 1,000. 1 over 100. 0. What? So this Henry H, 10 millihenry is equal to what? 0.0 what? Henry. So here becomes what? 0.01. So what's the answer now? 3.25 times 10 raised to the power what? Minus 1. There's no 5 there, and the answer should be what? Joules. Now, in inductors or inductance, there are 2 types. There are what? 2. When is your JAMB date? When is your JAMB date? April. And we are already in what? March. So don't be angry that this man is talking too much. I'm training. This is the fastest way you can learn. Some of you know how physics teacher from SS1 to SS3. Yes. And you are here. 2 of us. Yes. 2 of us. Yes. Some of you, this is the first time in your life you are hearing Henry. When they say Henry, somebody say somebody's name. I am going to write what? JAMB. Some of you, this is your second attempt in JAMB. They are here, they won't tell you. JAMB has already jammed them once. So better sit up and give yourself what? Brain. The truth be told, we are in a third world country, we are lagging behind. In the Western world, when they get to 16 years, they write an exam called Cambridge Edexcel. That exam takes them straight to Oxford, Harvard. They have everything. They don't play with education there. But yeah, the higher you go in education, the smaller your salary. Some people here at your level from SS3, they jumped to use the word jump, Abby. They go abroad. Not because their father won visa lottery. No, they wrote external exam and they were the best. The university, they will be calling them. The university will pay their ticket money, visa, accommodation, give them scholarship. Because they were what? They were the best. They write O-level. They write A-level. All the secondary school, Paco secondary school that we have here, when they do O-level, they're finished. Is that the end? You write O-level, write A-level, go and write AS level, and know whether you are okay. When you pass it, you will not be calling school. School will be doing what? Calling you. These inductors that we're talking about, they are of 2 types. What are the 2 types? We have self-inductance and we have mutual inductance. Hello? We have what? Self-inductance and we have what? Mutual inductance. So what is self-inductance? What is self-inductance? Anybody? Have you heard of self-inductance before? We said inductance, the ability of a device to store electrical energy.
Okay, so self-inductance.
So self-inductance during the production of induced EMF, the ability for that what? For the electric carrying conductor to store what? Electrical or induced EMF. Inductance here is given as what? The induced EMF divided by what? The rate of change. Second type of inductance that we have is called what? Mutual what? Inductance. Anytime you hear the word mutual, mutual is always about two or more persons. She is my mutual friend. What does it mean? It means that we have a particular friend in common. If she's my mutual friend, if she's a friend to this guy, and I'm also a friend to this guy, it then means that she is my mutual what? Friend. So with that knowledge, what can you think mutual inductance will be? An inductance that is caused by an EMF in a circuit, causing another circuit to be what? Induced. So the other circuit is turned on due to what? The induced EMF from the previous what? Circuits. Can you see that? So most times, if we have two electric carrying conductors and they are being connected, one of them producing an EMF due to what? Electromagnetic induction. The other one will also be what? Induced due to the first one.
What's going on here?
What's funny?
Shut up.
So I'm going to write this one as L subscript S, self-inductance. We also measure the what? Henry. This formula is different from this. This one is energy stored. Yeah, different from here. This one has another formula. So I'm going to bring out formula for this one. In fact, this mutual inductance has three formulas. This one inductance has how many formulas? Come again? I said it in the class. First of all, you must know what an alternator is. Alternator is an AC or AC current. So dynamo is a what? DC current. How do you change AC to DC? By changing the what? Slip rings to what? Split rings. Yes, DC generator. Rings. And if you want to do the reverse. This is I. This is I. So So take a look at this. Hello, young ladies. You asked me a question. Are they related? I said yes. You look at it. This is self. There's nothing. There's no A or B here. Yeah, this mutual inductance has to do with two coils. One of them is the primary, the other is the secondary. It is the induced EMF in the primary that brings about the what? The inductance in the what? The induced EMF in the primary causes the secondary coil to also be what? Induced. So I'm labeling my primary coil as A and my secondary coil as what? B. Now look at how the formula here looks like. So for us to have mutual inductance, the EMF that is flowing in B is caused about by the rate of change of the current in A with respect to what? Time. So if I want to get the EMF in B, all I need to do is to make B the subject of what? Formula. So I can say the EMF or the current that is being produced in B therefore is the same thing as what? Mutual inductance times the rate of change in current of A with respect to what? Time. This is just formula what? One. Just one formula. Can you see that? This is the first formula for this. We have another formula for induced EMF. In this EMF, mutual as M can also be given as what? Can also be given as mu N subscript A, N subscript B, all over what? L. This is the second formula for mutual inductance. The third formula for mutual inductance is M is equal to the square root of where L subscript A and L subscript B are the self-inductances of coil A and B, or self-inductances of the primary and secondary coil respectively. So in finding mutual inductance, you can either use this, or use this, depending on what parameters you are being given. So today what have we learned? If there are no more questions. You still have questions?
Yes.
Okay. So I'm going to take 5 more questions. 5. Yes. So out of the 5, if you give me one, you cannot give me one again. Another person. So let's have you. Please give way so that you can come out. The 2 of you, are you part of this class? Are you part of this class? The girl of glasses, are you part of this class? Bend down your head. Are you part of this class? You know what? Where I will know whether you have been listening is after the 5 questions. Me, I will not ask my own question. I'll just come to you and pick you. So if you are not able to answer my question, you have a battle with Mr. Sijuade. I know it's to waste my voice, so I know it's to waste my voice. My brain, I cannot sell it. I cannot sell my brain. I cannot talk for nothing. So while I'm teaching, you are gisting, you're telling her your own story, super story. You answer me, don't worry. Oh yeah. Read it out. Let's know the year. 2024. Question 8. Question 8. 2024. Yeah. What is the field density? This is the type I've been waiting for. What is the what? Flux density. Now, anytime we have flux density, that means we are looking for letter what? B. Okay, so which part can I clean up? This part. Okay, so what is the flux density? So we are looking for what? Letter what? B. I hope you know flux density is measured in what? Tesla. Okay, go ahead. Whose what? Whose magnetic flux?
1,500 microweber and a conducting surface.
Microweber. Okay. 1,000 what? 500 MW.
And a conducting surface area of 0.5.
Surface area of what?
0.5
meter square. So what is the what? Magnetic what? You're not reading well now.
What is the flux density of magnetic field? Whose flux is 1,500 microweber and a conducting surface area of 0.5 meters square.
Whose flux is this?
Yes.
Is that the word flux?
Yes.
And the area is what? This. Now, don't go. It's either that word is a typographical error there. How can you are looking for magnetic flux density and you are being given the flux to be what? In microweber. What I know that is in Weber or microweber is the what? Is the rate of what? Change. Respect to time. This is microweber, isn't it? Abi? Is that not what they put it? I'm asking you now, is that not what they said? MW, right? What did they put it? 1,500 watts. Okay. Flux density, this area is absolute. Okay. So MW means microweber, is the same thing. But this is the flux. But this one is the flux density. Do you understand? So, you don't understand? Okay, so there's only one formula that relates all of this together. So we have this is related with what? BAN cos theta. That other one, you can get the other one from this one. Was there any angle? If no angle given, it means that there's no angle between the flux and the velocity of the charge that meets with this. But what we have A, which is the area. We have what? N, number of turns. We have number of turns there. Was number of turns given? No. But we have this, isn't it? So in this formula, there's no angle. There's no cos. So I, when theta is what? 0, this formula is what? BA what? N. Magnetic flux density, area, and number of what? Turns. But you can see that there is no number of turns. So already we are looking for what? B. This is already what? 1,500. B times what? The area is what? 0.5. So what is B? 0.5. So it means that in this question there is no angle. The angle is what? 0. So B.
The microweber.
We already used it now, 1,005 microweber. Okay, we want us to change it to Weber. No, leave it like that. Yes. But another way you can know if they change it, because sometimes you check the options. If you look at the options, you will know if they have changed this microweber to what? To Weber. You will know. Because either in your option, the answer may look smaller than what you got.
Sometimes they do put distractors. They may be one now.
Yes, and sometimes they may put the one they converted and the one they may not convert. So it's always good to do what? Convert. In this one, did they convert it? No. They left it like that. So this Tesla now will be what? Micro Tesla. This magnetic flux density now, the unit for this one now will not be what? Micro Tesla, because the rate of change was in what? Micro. If they give us the angle, you use the formula. If they say this is 60, here will be what? VAN times what? Cos 60. Where N will be what? Number of what? Turns. But number of turns is not given. VA. You understand? There's no number of turns. If for example, okay, no, when we are proving the other, when we are proving the one of sine, I will show you something. So, one question has gone out of 5. 2005. 2025. 2025. Hey, question what? 37.
A transformer is rated 240 volts.
A transformer is rated 240 volts. What does this mean? A transformer is rated 240 volts. What does it mean? Hey! So if I buy this bulb now, and I say this bulb is rated 100 watts, what does it mean? I know it's the power, but what does it mean? The output, what this bulb can give me is 100 watts. So now, that transformer is rated what? 240 volts. What this transformer can give you is what? 240. That means the output is what? If you are reading, read with sense. How much is Ronaldo rated? How much is Ronaldo rated? Nobody know. How much is Messi rated? As of today, 9 million. Is it pounds? 700 million what? Dollars. That is what Messi is what? Rated. As at what? Today. That is Messi's output. Is what? Is rated what? 700 million. So this transformer that we're talking about is rated what? 240 what? Volts. That means the output is what? 240 volts. Meaning that VS is what? 240. Okay, continue.
If the primary coil is 4,000
If the primary coil is what?
4,000
Tons. So MP is what? 4,000.
Secondary voltage is
Secondary voltage, that's VS, is what? Secondary voltage is what? 12 volts. Are you sure? Read it again. No? Secondary voltage is what? 12 volts. Okay. Is it what? 12 volts. Oh yeah, continue.
That means
Number of turns in the secondary coils. Read this question in the beginning.
If the primary coil is 4,000 tons and the secondary voltage is 12 volts, the primary number of tons
in the what? In the secondary coil. So that word rated is input. That's the only way we can get this. It's input, not output. So this is VP. So it's rated. That is the what? Input. So it's very simple now. So what do we have? VS, VP equals to what? NS, NP, isn't it? So what's VS? 12. VP, 240. equals NS. We don't know NS. MP 4,000. NS becomes what? Can you see that? 200 what? Tons. So 2 questions gone. Remaining 3 questions. Okay, have you given us 1 out of the 5? Oh yeah, let's have it. What year? What year? Huh? 2020, number 6. Okay. What is the effect of what? Please stand up. Let's hear you. What is the effect of using split ring in a simple DC generator? Option A. Okay. The turns in the coil become what? Alternating. The one that has alternating, that's the correct answer. You know, I've always told you, when in a simple DC, you change the slip rings to split ring, you have changed a DC motor to what? An AC motor. So that is gone. How many questions gone so far? So remain 2. No, you guys have given. Who has not given question? 2. 1, yeah. Diagram, very good. Let's have the diagram. What's your name? What's your name? Fawaz. Fawaz. Huh? 2006. Question what? Oh, Fawaz. It was a diagram, Abi. Bring the book, let's draw it. Very good. So we have 4 diagrams there. For us, come and take. Okay, so the question says we have 4. This is option A, B, C, and D. That's which of the following diagram represents the magnetic field of 2 isolated unlike poles. Look at that one. 2 isolated unlike poles. First of all, we know what unlike poles are. When we have north, when we have south. So we are supposed to have force of attraction. That means option A and C, they are not part of it. So we have eliminated these 2. We now have this. They now say 2 words isolated. But if you take a look at option B and D, they look alike now. They look alike. Who can tell me the difference? Wait. Everybody here. This front, you are exempted from answering. Wait. This place too, you are exempted from answering. See, where I know that you are having concentration is up to the middle. So this middle, you can answer me. This back, you are on your own. This is another film. You know that if you are watching a film, inside the film there's another film. Another film did this so. Me, in my life, I can never the back seat. In my life, in my whole life, it's better I stay here. It's better I stay here, or I stay here, or I hang than for me to sit at the butt back. These people, can you answer me? We have already eliminated option A and C because they are what? Force of repulsion. And they have what? Light charges or light charges. We have S and N. In fact, all of them are what? Or light charges. But the drawing for A and C is wrong. Because the field lines or magnetic field lines supposed to have a force of what? Attraction. You see that? So now we are now left with option what? B and D. So who can spot the difference in option B and D? Yes. The direction, the arrow. You know what I was telling you? That the arrow will really help you. So what do you understand by the imaginary lines of force of a magnetic field? They always move from the north to the south. So which one is correct? So 4 questions gone. The last question. The last question, number 5. Question number 5. What year? Tell us the year and the number. 2010. Number 42. 2 words, 2 inductors. Oh, God bless you. Of inductances. Let's make one of the inductance to be A and the other one to be what? B. So the first one, inductance A is what? 5 millihenry. Inductance B is what? 1.5 what? Millihenry. Are connected in what? what? Series. God bless you.
And a current of 5 amperes.
And a current of 5 amperes flows through them, both of them, isn't it? Okay. Good. Total energy stored. So the total energy stored is going to be a combination of the total energy stored in A and the total energy stored in what? B. And remember, what is energy stored? What is energy stored in inductor? What is energy stored? Energy stored or total energy stored will become what? Half L I square, but for A, the I is the same going through the two of them. It's the same current that's going through the two of them. Plus the other one for B, half what? LB I what? Squared. Can you see that? Because we have two cores, A and B. But now, the units of the both of them are what? Meaning what? What do we do to them? Convert them. So this one will give me what? Divide by what? Divide by 1,000. So that be what? 0.005. 0.005 Henry, isn't it? The second one will be what? 1.5 divided by 1,000. 0.15. Please cross check it. Is this correct? So we have changed it to Henry, isn't it? $1,000. Are you sure it's correct? 1.5 divided by 1,000. Check it again. Who is pressing the calculator? Check it. That's minus here. Okay, so can we include it in the formula now? So this becomes what? Half inductance of A. 0.005 times what is I squared? 5 squared is what? 25 plus what do we have again? Half times in this one 0.0015 times what? 25. So the answer for this and this, you add it together to give you a what? Total energy stored in the what? In the what? Two inductors. Energy stored. Energy stored. Is it how you know to see my thing? Energy what? Stored in inductor. Okay, so we divide this section into 3. 2 questions for each section. I'm the one giving the question now. The button has been what? Changed. Your question time is what? Over. So this section has 2 questions. One for this side, one for this side. This section has 2 questions. One for this side, one for this side. The last section has 2 questions. One for this side, one for this side. Are we ready? Are we ready? Are we ready? Are we ready? Do you know what? In the Navy, they used to say onward together. What does it mean? Their motto in Nigerian Navy is what? Onward together. What does onward together mean? It means that both in success and in failure, everybody is going to carry the cross. On a ship, if one person make mistake, everybody will do what? Die. We are on a ship now. If one person fail or one section fail, everybody in that section will answer to Mr. Sijuade today. I know him. He's a disciplinarian. I can tell him that those blocks that are there, you carry it on your head like this from 9 to 6 p.m. And he will agree. Are you ready? Are you ready? Are you ready? Okay, can somebody tear 3 pieces of paper for me? If you pick, we start with that section. What is section 1, 2, and 3? Whichever one picks first, we do section first. Can you tear 3 pieces of paper for me? Write 1, 2, 3 on them. Is what? It's 15. Okay, in the they said in the textbook, in the last question, this thing is what? 15. 15 divided by 1,000. 0.015. So in the past question, this thing is 15. So 0.015. Okay, so yeah, you've written 1, 2, 3, and 1, 2, and 3, right? Don't be scared now. It's not. I won't ask you anything other than what I've just taught you. So, who is speaking for us here? Who is speaking for us here? Come out. The author, go out. Who is speaking for us here? Who is speaking for us here? Abdullah, go outside. Go outside, fast. Who is speaking for us here? Who's speaking for us here? This guy. Oh, yeah, go outside. No, it's not better. We are just speaking. Just speak and go. I just say answer question. Go outside, Jare. Where are you? Come and pick for them. Come. Be careful. Who is speaking for you here? Okay, come outside. Come outside. Come. Hello. 3 rules. Number 1, there's time for. Number 2, don't disturb me in my class. Number 3, obey rule number 1 and number 2. This life is very simple. How do you used to do it? There will blow breeze, Abby. Should they pick by their height? Or should we do ladies first?
Yes, ladies first.
Let's be gentlemen. Let's respect our ladies. Okay, so ladies first. So what have you picked? Whatever you pick, we go first. One is 1. Group 1. 2 questions. Go sit down. Each group. This is group 1. Group 1 is made up of left and right hand side. How many ears do you have? 2. How many eyes do you have? How many nostrils do you have? How many gender do we have? 2. We have day and night. Everything in this life is what? 2. Good and bad. Small and big. Tall and short. Right and big. Male and female. Group 2. 2 is second. This will go first, second. Group 3. And you are in group what? You are in group 2. So you go the second time. Can I clean this one? Yes, sir. Can I clean this one? You know that in a question, some of the might be on the, so I have to clean it now. So the question will not be far from what I just taught you today. No. See, you know this group 1, we have left and right hand side. This left hand side, all of you will join your brain together. You just as you chose what's her name? You will choose one person that will answer for you. But the answer, she's speaking for what? All of you. Do you understand? She's a speaker, but it is whatever you tell her to say, that's what she will want to say. The same thing with you. Do you get? When you used to go for a break? 12. Okay, so we have 30 minutes to go for this exercise. Hello? Rule number 1. There is time for what? Rule number 2. Don't disturb me in my class. Rule number 3. Obey rule number 1 and rule number 2. Here's my first day. I don't want to be asked. They see me now and say this man is very wicked. I don't like that. But me, I'm warning you now. The best thing for you to do is to listen to the question they gave another group, so that tomorrow it might be your turn. The good thing about this question is that you are working in groups. This is what we call group activity. What does it do? It helps us to know how well we understood the topic of that very day. I didn't give you assignment to go and solve or go. We already have past questions for that. But we want to do group in class what activity. Something that triggers your brain. Who is going to be answering for this group 2? Remember, A is on the right hand, B is on the left hand side. So who is answering for you here? It is a group activity. All of you will put your heads together and you tell the person that you want to answer. And you only have 1 minute to do that. This side too is a group activity. Who is answering for you? Are you sitting on the chair? Are you on the chair? You don't want to ride on that table. This who is going to talk for you? You know that this group stops here. Sure you know. This group stops here. I'm talking of from here. No, this group stops here now, this pillar. So from here now. So who is answering for you? People on the Chelsea, answer for them. So you put us together, you tell us, you answer 1 minute. Who is answering for this guy? Okay, Henry. So for the back group, this A, this is what? B. For B, who is answering for you guys? Are you the one? You're in group 2 or group 1? Group 3. You're in this group. So you are going to be answering for them. 1 minute. You put hands together and they tell you what you want. Say. This group, who is answering for you? Who? Grace. Who is Grace? Talk now. Who is answering for you? Huh? Where is he? Okay, you answer for them. 1 minute. All of you put hands together and then you answer. Now, listen. They usually say that you are as strong as your what? Weakest link. You are as strong as your what? Weakest link. What does that mean? It means that your strength as a group lies in the weakest person that you have there. If that person fails you, the ship will do what? Sink. It's always good to participate in class because some things you hear in class cannot be found in your what? Book. Are we ready? Are we ready? So, by the way they pick the questions, or by the way they picked just now, group 1 is going first, and they have 2 questions. So we start with A. A is on my right hand side.
Yes.
So A, are you ready? You have what? 1 minute. I need a timekeeper. Please note that all of you on this side, you people belong to this group. From this girl, you belong to this group. From you belong to that. The 3 of you like this belong to this group. So I need a timekeeper. Come now. Can you help me watch?
That's what I'm going on. Let me do it. I want to watch it. I want to watch it.
Don't worry. Can you know what 1 minute is? 1 minute. Please let's put our hands together for our timekeeper. If not, you can sit down. You look down and sit down. Our job is to say what? Time up. Hello? There is time for what? Don't disturb me. Obey rule number 1. Our job is very simple. Our job is just to say time up. Once you say time up, if she says time up and that group does not get the answer, the other group have an opportunity to work. Not group 2, the A part, the B part. Do you understand? The B part will have an opportunity, 1 minute, to answer that question. Then if this B part cannot answer the question, group 2 and group 3 have an opportunity to answer the what? Question, all within 1 minute. Use it now. No cheating. This is your question. When I say start, you look at the time. Start. 1 minute. Hey. Once the time is up, just tell me time up. Where is your speaker? Who is the person? Where is your speaker? Stand up. Oh yeah. I go. What is the hygrometer? Humidity. Does it have anything to do with electromagnetic induction? God bless you. As a group, you are good to what? Go.
Shut up! Emmanuel! You speak nonsense. You cannot make sense out of your nonsense. You cannot make sense out of your nonsense. This guy is a baba. Shut up! This one is baba.
Please, come on, goes. Okay, you are another group. Who's another? Go and get me marker, please. Start.
The height of the amateur.
Final answer.
Yes.
Final answer.
Yes.
The height of the amateur is what? Because this says does not. As a group, you are good to what?
What did he say? He said, I think it's
Who goes second? Group 2, Abi? You are in group 2. And come to your group now. Where does group 2 start from? From this side, Abi? This what? This group 3. This group 2. Group 2 has A and B. Okay, you chose 3. Okay, you chose 3. Okay, so group 3 will answer first before you guys, Abi? You chose last now. So the next question goes for what? Group 3. And group 3 will have A and what? B. Thank you. Can you hear me now? Group 3. Hello? Hello? 3 rules. There's time for what? Don't disturb me. Obey rule 1 and rule. See, when you are doing your own, they listen, they give you time to think. Allow them to what? Think. Group 3, we are starting with A. Where is that? You are here. I thought you are in school. Okay, you only wrote WAEC. She was in that last set. So who's speaking for them? Good. Listen carefully. Listen carefully. I should write it on the board, Abi? Okay. Listen. Hello? Listen, sit down. Hello? What now? What is it now? Yes. So we have two calls, X and Y. And this is a what? This is a what? Lamp. This is an ammeter. In the above, two coils, X and Y, are connected along the same axis. Which of the following is a reason for the lamp in circuit Y to be what? To be turned on? When the switch in circuit X is switched on. Option A. Option B. Option C. Option D. Option E. So group 3, where are you? I'll give us the reason why. No, what's the answer? Their time is counting, oh. Their time is counting. 1 minute.
1 minute.
Their hands together is what they told you that you will say. See, when their time is up, tell me time up. D, what is D? Electromagnetic what? Why?
When you flip the circuit of X, it creates a magnetic field around Y.
Please put us together for this guy. I told you in the class that if 2 circuits are connected, X and Y, the other one will be induced due to the what? The primary what? Coil. This is the primary one, this is the secondary one. When you turn on the switch here, the other one will be induced because of what? This one, thus making the light here to go on. 1 point. Option what? D. Electromagnetic what? Induction. Huh? There's got one. Group 3. They are the one at the back. So for you guys, B, Abi, who is your spokesman? What's your name? Huh? Eliazar, handsome guy. Hello. Hello. Eliazar. Group B, your question will be as a result of this question. Listen, since you all have agreed that when we switch in the circuit A is turned on, it automatically turns on the lamp in circuit what? Y. Now, if the distance between circuit X and Y is increased, what will happen? Be thinking of option A, the lamp in Y will go off. Option B, the lamp in Y will be dimmer. Option C, the lamp in Y will be brighter. Option D, the two circuits will explode. All these things are JAMB questions. Now JAMB they give you. Start. Your time is up there. Your time has ended. What is that your name, Eliezer? Your time is going. Oh yeah, tell us and tell us why. Listen, talk to yourself. You can't tell me. If the time is up, tell me. If they just lose that. Oh yeah. The lamp in Y will do what? Why?
Both X and Y, they are attracted by magnetic force.
Yes.
So when the distance between them increases, the magnetic force will fire weaker. The strength of the magnetic force.
No, he gave the answer first. Listen, he gave the answer first. He was not giving the explanation when the time went up. Nice one. What you would have just said, I know. The reason is simply because induced current is inversely proportional to what? Distance. So, the greater the distance, the smaller the what? Induced current. So, if the induced current is smaller, that light will go dimmer. You are good to what? Go. See, it's not by who went to police station first that used to win the case. So, you know, initially I wrote them off. I told them that they were a film inside another film. Now don't give answer. Don't underestimate anybody. Don't judge a book by its cover. I thought that as they are sitting there, maybe they are not listening or they are doing another thing. Now don't give answer with reason. You don't fear now. So middle group, Abi, the ball is in your. Are you scared? Are you scared? Just talk to yourself. Eh? You are A, Abi? So the last question for A and B, group 2. If you guys will not get anything, it will be your group that will go and meet him. Okay, we are moving. Okay, hold on, I'll soon be done. Yeah. Okay, now we'll see. Wait, you're not saying question, you're already shouting. Hello, come back to your seat. Fast now. Why are you shouting? I'm not saying question now. Very simple now. Anything that they say straight is very simple. Auntie, sit down well. Why are you shouting now? So, I'm starting your time. Start. Hello. Rule number 1. There is time for what? Don't disturb me. Number 3. Obey rule number 1 and rule number 2. Hello. Start. Okay, say the formula, say it out. The phi, the t. Okay, so state your parameters. What are they? I don't know what is I. I don't know. Rate of change. Good. The flux linkage. Thank you. God bless you. She was very well correct. She stated the formula. She stated the definition, and she explained using the word formula. And she told us the meaning of I, the induced EMF. She told us N, number of turns, and she told us the I dt is what? The rate of change of what? The magnetic field or flux linking the what? The coil. Also, what you should know is that the rate of change, the unit for the rate of change is what? Weber per seconds. The unit for the I dt is Weber per seconds. So the last question. That is for group what? B. Where are you? Spokesman, stand up. This is my guy who was here in the last session. My guy who. You know, I told you once in your life, there's always two. We have a male and a female that was here last session. They can tell you a bit about it. It was tough. It was tough. So guys, it's a group activity, work together. Your question will be as a result of these people's what question. See that, you're blocking us. Hello, I don't like that noise now. What's wrong with you? Hello, I don't like it. I'm warning you now. There's time for what? Everything. Hello. There's time for what? Start. Oh yeah. And you tell us why. You tell us what? Why? Talk to him. Talk to them, because there's nothing. I will not give you another option. Talk to them. Is the time on? Is that your final option? Why? Explain. Why?
It flows in the opposite direction of the
When your time is up, tell me. Time is up. Hold on. Sit down. Hold on. Why did not give the answer out? Because he got the question, but he failed the explanation. What did you choose? E. Truly, out of all of this, it is only option E that obeys the law of conservation of what? Do you know the reason why? Anytime an induced current is being produced, energy is being expended, work is being done. Despite the fact that the motion of that induced current moves in an opposite direction, does not imply the fact that it obeys conservation of energy. Why does this law state? This law states that energy can either be what? Destroyed, created, or transformed from one form to another. Have you always observed that in all or most of the examples of electromagnetic induction, they always produce what? Or move from one form of energy to the other. Because of this law, you can have mechanical energy changing to what? Electrical energy. At the same time, you can have electrical energy changing to what? Mechanical energy. Because of what? Lenz law. It's not because of the fact that the motion of the induced current moves in the opposite what? Direction. If you say that it's only one way, if it moves in the opposite direction, it means that you need an opposite and equal reaction force to move your magnet back into the what? Into the what? Magnetic what? Field. You see that? So as the induced current is pushing out the magnet, you need another equal and opposite force to push the magnet back into the what? Electromagnetic what? Field. You see it? So this is the only law out of all of them that obeys or corresponds to the law of what? Conservation of what? Energy. Thank you so much. What's your name? Go and sit down. Please put your hands together for yourself. Put your hands together for yourself. Listen, after today, I want to come back to a class where everybody's up and going. Everybody's asking questions. Everybody is solving. Everybody saying, why is this? Why is this? Why is this? Not just a few people. I want to come back to a class whereby, before I talk, you already know what I want to say. It happens. It means that you and I are on the same page. It means that you and I are what? On the same page. So I was told that I used to have break by 12. I think it's 12. So everybody can go on break. I don't know if your director says. But on Thursday I'll be here.